looking at a few checkpoint questions and just kind of recalling some of the initial events of differentiating graded potentials, some action potentials, talking about the change in the permeability of the membrane to sodium and what event of the action potential that's responsible for. And then speaking about specifically the gating mechanisms for some of our ion channels and how that also applies to the movement of these ions and therefore the generation of the action potential. So we're going to keep on moving here along this packet. And as I mentioned before, this is really just different perspectives of explaining the action potential. So we talked about the graded potential a little bit. We spoke about the gating mechanisms of sodium, of potassium, and then we talked about depolarization versus hyperpolarization versus repolarization. And so we're just looking at the same idea of the action potential, but just from different perspective, right? From different viewpoints. And so here we're going to look at the action potential from the viewpoint of the membrane permeability, okay? But we want to remember here, this is all the same thing. The membrane permeability is the same thing as which ion channels are open, which is the same thing as the movement of these ions, right? They're all connected in terms of applying to the same events of the action potential, but just different ways of looking at that. And so here what we can see is basically a depolarization of an axon and how that allows sodium to diffuse into the cell. So we open up those voltage gated sodium channels that allows sodium to move into the cell, and that is what is responsible for the depolarization. So they're just kind of different sides of the exact same coin. The channels that are open, the movement of the ion, and then the depolarizing event, which is brought about as a result of the movement of that ion. Okay, and so that is a depolarization event that is going to make the membrane potential go from -70 all the way up to +30. And remember why it's moving in that direction. One, because the ECDF of sodium is inward. Okay, so that's going to make a positive membrane potential change as sodium is a positively charged ion. And as it is also moving toward its equilibrium potential, which is +60. So in doing so, it rushes into the cell according to its strong ECDF, and that facilitates the depolarization of the neuron. And then we've also got the repolarization of the neuron, right? The opposite side of these events. So essentially we have the, when the membrane potential reaches +30, this is a trigger for the closure of the sodium channels, the opening up of the potassium channels. And so we basically reverse the membrane potential. We create the movement of a different ion here. So potassium is now moving. And remember, potassium has a different direction according to its ECDF. Potassium is also positively charged, but it's moving out of the cell. And when it does so, it leaves behind more negative charge as it tries to approach its equilibrium potential, which is -94. And so as these potassium channels open, because of that specific voltage requirement, we now see potassium leaving the cell, which leads to less depolarization or repolarization as we restore that resting membrane potential. And so according to those events, we go from +30, which is the peak of our action potential, back down to -70, which is rest, okay? And looking at those events as they apply here on this graph, we see the graded stimuli. So remember, those graded potentials are the stimuli that help us to get to that equilibrium, that threshold value, -55. And then from there, it's an all or nothing phenomenon, right? It's going to happen. We're going to open up those sodium channels. That is a positive feedback event. So when one channel opens, it opens another channel and another channel and another channel. The membrane potential spikes, and then we reverse those events at +30 and result in the repolarization because of the movement of potassium here. And we get back down. We slightly go under that resting value, slightly, and then we go back up to that -70. Okay. And I also want to point out the timed component of everything that's happening here. So an action potential is anywhere from 1 to about 3 milliseconds, right? So a very short phase of time. And it is always that amount of time. Action potentials are always the exact same amplitude in terms of the change, right? The value of the change, it's always to positive 30 and back down, but then they're always the exact same time in space, right? So they always happen for this 2 to 3 milliseconds. So let's speak here about how the membrane permeability is changing. And the membrane permeability is just a reflection, right? We keep making this point. It's just a reflection of which ion channels are open versus which ones are closed. So we know that at rest, because of the fact that there are more leak potassium channels, the membrane permeability for potassium is greater than the membrane permeability for sodium. Okay, this is why also at rest, the membrane potential looks more like the equilibrium potential for potassium and is really far away from the equilibrium potential for sodium. Okay, something we've already spoken about. And so this is what we are, this is where we are at rest. Now, during the depolarization to threshold, because of graded potentials, we get closer to our threshold value. And if we meet that threshold value, if we have strong enough of a stimulus or several stimuli that are summed, that are strong enough to get us to that threshold, we then open up our sodium channels. And what we see here is an increase in the membrane permeability for sodium. Okay, so this purple curve is showing that increased permeability for sodium going up. And then that is the depolarizing event of our action potential, which is this pink curve. Now that will then trigger this regenerative mechanism in that opening up of one sodium channel triggers the opening up of several sodium channels. This is what causes the action potential to keep propagating down the length of our neuron. And then we see the slow closing of sodium channels and then the slow opening of potassium channels when we get to the peak of our curve here. So at positive 30, we see a flip-flopping of these events. The sodium channels open, the sodium channels close, potassium channels open, and then we see the opposite movement, right? The permeability for sodium decreases. Initially, we had a very low permeability for potassium, but now here, right at that positive 30, the permeability for potassium starts increasing, okay? And remember, it's that increase in permeability, that increase in movement of potassium that creates this downward slope of the action potential, all right? And so that is what gives us the upward curve for our action potential and then the downward slope of our action potential. Now, can anyone remember which of the gates on our sodium channels is responsible for or closes at positive 30? Can anyone remember the gating mechanism that happens at positive 30? So which of our gates are open and which of them are closed at that positive 30?
At positive 30, that's repolarization, I believe. And the activation gate is open, but the inactive gate is closed, which causes sodium not able to pass through at all. Excellent. And not even a stimulus can open it.
Excellent, perfect. I'm glad you added that at the end there. So even if we tried, even if we had a strong enough stimulus, a negative 55 or more stimulus, we cannot supersede the inactivation gate being closed. So if the activation gate is open, inactivation gate is closed, which is what happens at positive 30, then even if we wanted to, we could not fire a subsequent action potential. Okay, really important. Okay, and then we're looking here at repolarization. So repolarization is the downward slope that's created by the movement of potassium. but we also want to point out that it slightly goes below that membrane, below that resting membrane potential. So potassium channels remain open beyond the resting membrane potential. And so potassium is still leaving, right? It's still trying to approach its equilibrium potential. And so this is why we slightly go lower than that resting membrane potential. And then when we almost get to potassium's equilibrium potential, then we have that restoration of the resting membrane potential really by the closure of those potassium channels eventually, but also more importantly, by the sodium potassium pump that kind of resets all of this and brings us back to our resting membrane potential. Okay, so here we have that sodium potassium pump that kind of kicks in or chimes in and restores our, so here in that pink curve, this is our slight hyperpolarization, so slightly lower than rest. And then when all of the potassium channels eventually close, and we can see that because the permeability has flatlined here once again, okay? And now the sodium potassium pump kicks in, we can now reestablish the resting membrane potential, and we see the membrane potential get back to -70, okay? So here's what's happening after hyperpolarization. So the membrane slightly overshoots the rest, which is what we just described. It goes down to about -85 or so. And then it is restored with the sodium potassium pumps, which basically prevents the membrane potential from getting to -94. It's trying to get to potassium's equilibrium potential, which is -94. And that is a reflection of the fact that potassium channels are still actively open. And so until they fully close, the membrane potential still keeps falling. When they all fully close, along with the sodium potassium pump, quickly reestablishing that resting value is when we see the membrane potential get back to -70. All right, so that's just explaining what the difference is between repolarization and hyperpolarization. So hyperpolarization, we said, was a movement that goes away from our set point. So anytime membrane potential goes more negative than -70, that is considered hyperpolarization. Whereas if it's trying to approach -70, that is considered repolarization. Okay. All right, so I'm going to pause here just a little and see what questions we have so far. And then we will keep moving. Okay, so now we will begin to sort of add some character to the action potential. Speak about some of the properties that govern the action potential. So first of all, the action potential is all or none. This is the all or none principle. And what that means is we speak about this threshold value, right? It's the minimum requirement to depolarize the neuron in order to fire or initiate an action potential. And so it induces this regenerative mechanism for the opening up of sodium channels. And what I mean by that is the fact that if I open up one sodium channel, if I get to -55 and I open up one sodium channel, I don't need to maintain that stimulus, right? The opening up of a single voltage gated sodium channel is regenerative. In other words, if I open one, I'm going to create the events that will allow the future or the other sodium channels to open up. And so all I need to do is get to that threshold of -55, and then the rest will take care of itself. Okay, that's what regenerative mechanism means. And that's what we mean by being that minimum depolarization requirement. Okay, and so if I have a sub-threshold stimulus, there is no action potential. So if I don't get to that -55, let's say I have a -60, a -56, right? I'm not going to fire an action potential. I'm not going to open up that voltage gated channel. If I have a supra-threshold stimulus, which is a really strong stimulus, I'm not going to create a stronger action potential, right? There's no such thing. It's really just that minimum threshold requirement. And as soon as I exceed that requirement, the action potentials will be exact same regardless of the magnitude of the stimulus, the type of the stimulus that is coming in, okay? So action potentials from a threshold and a super threshold stimuli are the exact same magnitude in terms of the strength. They only go up to positive 30, but then they're also the exact same amplitude in terms of the time. They only last for the exact same 1 to 2 or 3 milliseconds. Alrighty. And so what we're seeing here is sort of an illustration of that idea. We have a weak stimulus, okay? If we get to negative 55, we fire an action potential here. If I have a stimulus that is exactly negative 55, I fire the exact same action potential. And if I have a very strong stimulus that supersedes my threshold, let's say I had a stimulus that gave me 50 or 40 membrane potential value, or a change that approached that membrane potential value, I am going to generate the exact same action potential, okay? So this is what we mean by all or nothing. So I either meet the requirements to fire an action potential or I don't, okay? And it's gonna be the exact same action potential all the time. All right, so just kind of reiterating that same idea as we go on here on the future slides here. So the size of the stimulus does not affect the size of the action potential. It will always go up to positive 30. It will always last the same amount of time, and it will not affect the amplitude or the magnitude of the action potential. Okay, another illustration highlighting that same point. So we have one graded potential here, pretty small, another graded potential here. And if we sum these, right, if they are close enough in time, we can sum them, that's temporal summation. If they are close enough in space, we can sum them again, that is spatial summation. So we can add those together and that would get us to negative 55. And then we would fire an action potential here, okay? And so we're comparing the actual stimuli down here. So these two stimuli have been summed to give us this threshold stimulus that fires this action potential. And if we fired, or if we had a stronger stimulus, which is considered a super threshold stimulus, that would generate the exact same